Okay, so let's. Okay, so thank you everyone for coming back after lunch, and hopefully this session will go more smoothly. And our next speaker is Sofya Raskhodnikova from Boston University, and she'll tell us about properties testing with incomplete or manipulated inputs.
Thank you, Talia, for the introduction. And so this is based on joint works with my wonderful co-authors, Omri, Iden, Esty, Ephraim, Uri, and Nithin. But before I get into this, so do we have Dana listening? Or I don't know, is she actually there? Okay, I'll say a little bit. So I've always considered Dana my mentor and role model. And I do have 3 papers with her from times before. So my first paper was with Dana. And when I was a postdoc at Weizmann, I fondly remember trips to Tel Aviv to work with her, and 2 papers resulted from that also. Basically, so I'm very thankful to her for everything she has done for me. And she played a big role just as a role model. And this paper is on introducing a new model that is relatively new, and I guess just by itself, you can see influence of Dana in this. And I will leave my thanks to her for kind of the social time after this session. But so like, I'm just going to proceed with the talk. Yeah. Huh? Dana is here listening, great. So thank you, Dana. And so there's more social stuff for the social part. Okay, so, so the goal of research on sublinear algorithms is just fundamental understanding of sublinear computation. And specifically, in this talk, we're going to try to see which sublinear computations can become robust to adversarial online manipulations of the input. So that is, while the algorithm is computing, somebody is going to be tampering with the input. And specifically, we'll look at 2 types of manipulations: erasures and corruptions. So this is how we typically model access to data for sublinear algorithm. So the algorithm gets its input as some huge object, which it can access specific locations of. So it can make queries and get back the answers about what's written in that location. So this is the usual sublinear time algorithm. And now, to model this adversarial modifications to the input, we're going to give access to our sublinear time algorithm to its input via oracle, which we're going to call adversarial online oracle, which is going to modify the data as we go. And specifically in the case of erasures, it's going to be the online erasure oracle. Okay, so after answering each query, the oracle erases T input characters, where T is some parameter that's given to the algorithm, and it represents the erasure budget for the adversary. Okay, so here's an example. So the sublinear time algorithm is going to ask a question, make a query, it's going to get back the answer, and after that, the algorithm the oracle gets to erase T location. So in this case, T is equal to 1, so it got to erase 1 location. So the special symbol is representing an erasure. And then the algorithm is going to make another query, get back the answer, and the oracle is going to make another erasure, T erasures, and so on. And then if the algorithm happens to query a position which has been erased, it's just going to be told, okay, this position is erased. So the erasures are performed adversarially and online in response to actions of the algorithm. And sometimes it's very hard to model exactly what the situations that's happening. So worst case analysis is just a tool to use to understand very complex situations when we don't want to make assumptions. Oracle knows the description of the algorithm, but not its random bits. Okay, so this is the model for access to data in the case of erasures. And in the case of corruptions, we have online corruption oracle, which is defined exactly the same as the erasure oracle, except that instead of making erasures, it makes modifications to the data. And feel free to stop me and ask questions. at any point to just shout out your questions. So far, any questions? Yeah. Yeah, so it's erased afterwards, right? So it's better for the Oracle to erase it. So, okay, so there are some motivating scenarios. Maybe for the sake of time, I'm actually just going to show you the pretty pictures and not discuss it much. Okay, so our goal specifically is to study this adversarial oracles in the context of property testing. So this is the usual standard property testing model. Is there anybody who doesn't, who knows the property testing model? Everybody knows the property testing model. So this is the standard property testing model, right? So like yes instances have to be accepted with hyperability, no instances that are epsilon far have to be rejected with hyperability, the usual notion of distance. So just for the sake of comparison, I'm going to define offline adversarial models so we can just see how they compare with online adversarial models. But sorry, I forgot to mention. So what we're going to try to solve is this usual property testing problem with this adversarial online oracles. So we're going to ask what properties can we test with online erasure and corruption oracle, and how does complexity of testing depend on this budget of erasures T. So this is what we're going to try to solve. And now I'm going to define the offline modification models just so we have them as a point of comparison. Oh, and I forgot to mention, right? So I guess you can search, you can count how many different papers of Dana appear on the slides. So of course, property testing model is one of the gifts that Dana and her co-authors gave us. So here's another gift. So tolerant property testing model. So we have two parameters there, alpha less than epsilon. And of course, the algorithm has to accept inputs that are alpha close and reject inputs that are epsilon far. And one motivation for this model and one way of thinking about it is that the adversary can introduce up to alpha fraction of corruptions before the algorithm starts reading the input. So this is, in fact, an adversarial corruption model, but it's not online, right? So it's an offline model. Everything happens before the algorithm starts reading the input. And analogously to this, there is an erasure resilient model, which is also offline, and it's defined kind of analogously. So the adversary can introduce up to alpha fraction of the input, can erase up to alpha fraction of the input before the algorithm starts running. And so the inputs have to be accepted if they can be completed to yes instances. So if you can fill in the erasures to make it a yes instance, and they have to be rejected if any completion is epsilon far. So here's the plan for the rest of the talk. So we're going to start by discussing some classical properties that exhibit the extremes in terms of query complexity. And then we'll talk about separations between the models, and I guess we'll see if we get to other parts. Okay, so here are some properties which have been studied a lot and which exhibit some extreme behavior in this model. So some properties can be tested with the same query complexity as in the standard model, once for constant erasure budget T. And I'm going to focus on the erasures in the rest of the talk, and in a couple of places I'm going to mention corruptions. But we know much more, I guess, about erasures than corruptions. Okay, so some properties can be tested with the same query complexity, and some properties are impossible to test even when you have just one erasure. So in the first category, we have linearity of functions, and more generally, the property of low degree, which is being of degree at most d, where d is some parameter. And so even though we know that the dependence on epsilon here is the same as in the standard model, it's been difficult to pin down the dependence on t in the query complexity. And for the second extreme, we have the property of sortedness and the Lipschitz property of arrays. So they're very much testable in the offline models, but it turns out that they're impossible to test at all in this online model. And one takeaway, even from these results that we can get, is that even the simplest tests, for example, those that sample uniformly and independently at random, cannot necessarily be made resilient to online erasures, even if you are willing to take an overhead in query complexity. So for example, sortedness has a tester that just samples uniformly and independently at random. So it's not the best tester, but there is a tester like this, since it has sublinear query complexity. And it turns out it cannot be tested at all in this model. So another thing that we'll see is that the structure of violations to the property plays a role in determining the stability in these models. Yeah.
Just to, that has nothing to do on whether there's dependence on n or not. Right?
So whether there isn't a dependence on n or not in the original.
Yeah, it's not like, oh, they can be tested with the same complexity because they were independent on n, and they can't because.
No. So I guess we'll mention. So I'll talk about separations later. So there is a separation. So I guess not in general, right? So yeah, but I guess in this examples, yeah. So there are. Yeah, I guess I chose like properties that everybody knows of. But so for example, for sortedness, you can take a constant size alphabet, and it's still like, so it's testable with, in the usual model, in the standard model with constant query complexity, but not testable. Okay, so let's sorry. Let me take it back. So it depends, like it's complicated. So maybe let me just take. So, okay, so linearity testing. So this is our, yeah.
Let's say I ask for, like, let's say I don't care about something.
So I'll show you why. So this is actually a very simple reason why it cannot be tested. So I'll show you why it cannot be tested at all, right? So. But we'll get there. So first, let's talk about the properties that are easy to test, so like linearity. So so let's consider functions which are defined on n-bit strings and provide 0, 1 output, so Boolean functions. So such a function is linear if it can be represented as sum of the input bits for some subset of the coordinates. So this is one definition of linearity. And all computations here are over F2, right? So mod 2. And equivalently, a function is linear if f of x plus f of y is equal to f of x plus y for all pairs of points x and y in the domain. And in the standard model, of course, there is a famous test by Bloom, Lubin, Rubenfeld that was studied a lot in subsequent papers. And so this test gives 1 over epsilon has 1 over epsilon query complexities, and of course this is there's a matching lower bound, right? So this test has basically the best possible query complexity, and in the online erasures model, so we show that 1 over epsilon plus t queries is sufficient, and also there is a matching lower bound. So we understand the query complexity exactly for this problem. Okay, so let me just remind briefly what BLR Bloom, Lubin, and Rubenfeld tester does. So it samples points x and y from the domain uniformly and independently at random. Then it queries f on x, y, and x plus y. And then it rejects if this condition in the second characterization doesn't hold. Right, and you can repeat it enough times to get the right complexity. Okay, so what goes wrong if we try to run this tester in the online model? Oh, sorry, I forgot the order, right? So of course, it's clear that this tester always accepts functions that are linear. And the difficulty in analysis is to show that it rejects functions which are epsilon far. And at the core of the analysis is this theorem that shows that if the function is epsilon far, then at least an epsilon fraction of pairs x and y violate linearity. So you can choose a pair like this at random. And right, with probability roughly epsilon, you'll get a violation. So you can repeat it 1 over epsilon times, and this is your tester. Okay, so this is the classical BLR test. So what goes wrong if you look in the online model? So we'll query X, we'll get f of X, right? So like it's unlikely that the tester has erased a random point. The same for Y, but at this point, the oracle can safely erase X plus Y, and then we cannot run the test. Okay, so what can we do? So we prove a new structural theorem, and it says that if the function is epsilon far from linear, then for all even k, we can take, instead of just tuples of points, we can take k tuples of points and check if they violate linearity. So at least, so what does it mean that they violate linearity? So kind of analogously to the second characterization. So if we take the sum of the function values on these points, in a linear function, they would have to be equal to the function value on the sum, right? But they violate linearity if it doesn't happen. So, and we show that not just an epsilon fraction, but k epsilon fraction of them violate a linearity. Right? So it's a generalization of the structural theorem for BLR test.
You get log t because then you can do all combinations. Then and get 2 to the log t.
Yes, I'm going to go over it. Yeah, but that's good. Yeah, Arthur.
Theorem holds for odd k.
So for odd k, so it has to do with whether you have plus a constant there or not. So the way the linearity is defined, there's no plus constant is allowed. So because of with odd k, it's the issue with that it's going to accept things that it shouldn't. But yeah, I guess small things. Right. So it gives a lots more option for the algorithm. It says such that. So here's the algorithm. So first, we're going to query a reserve of k points, where k, roughly speaking, corresponds to our query complexity. And so why we're doing this? So we're trying to do this to fool the adversary, so the adversary doesn't know what to erase. And then we're going to sample a uniformly random subset of the indices of these points. And we're going to query y, which corresponds to the sum of these points, right? And we're going to check this condition given by the structural lemma. Right, so that's the test. And and implicitly, if all points are non-erased here, right? So we're going to reject only they violate linearity and they're not erased. Okay, so here's a simple example for erasure budget 2 and k equals to 4. So we query 1 point, maybe the tester, the oracle erases something. We query another point. At this point, the oracle can erase, so the edge represents the pair. And then we query another point. So the oracle has 2 erasures, so it can erase the corresponding pairs. And then if we query the 4th point, so maybe the oracle erases 2 of these pairs, but there are more choices for the queries, right? So there's a query that between these 2 points and the sum of all 4 points is still available to us. So even already at this point, we don't know what the tester, what the oracle would have erased, right? But we can try, and with probability 1/2, we're going to succeed. And of course, as we query more points, we get more options, right? And for k queries, there are now 2 to the k options for the last query, according to our structural theorem, instead of k squared that would be there with the BLR type structural theorem. Is it clear why the tester works intuitively? So like, I guess I didn't give the proof, right? So like, it's not enough to just to patch something of the right form. You also have to find the erased, sorry, you have to find the violated part. Yeah, but so there's some proof involved there, but hopefully you get the intuition. Okay, so let me give some takeaways from the analysis of the linearity tester. So this is our structural theorem. So first of all, it's proved via Fourier analysis, but I'm not going to show the proof. So another thing to note is, so even though our goal was to study the online model, it actually gives a new optimal linearity tester in the standard model. So you can query a k tuple of this form where k is theta 1 over epsilon and check if it violates linearity. And it gives you a tester So it's a kind of a different tester for the very well studied problem in the standard model. So another thing we prove is this no erasure lemma. So the tester is unlikely to query an erased point. And one of very few things we can say about corruptions in this model is, so there is a kind of the intuition for the proof here is, well, when we query uniformly random points, of course, we're unlikely to query an erased point. But even for the last point we query, there are still so many options that the tester could not have touched most of them. So if we pick uniformly at random, we're still unlikely to see an erased point. Okay, so, and the way we use this no erasure lemma is to show that our linearity tester is also online corruption resilient. So we can show that if you're not likely to see any points and not likely to make a mistake, right, then you can as well use your tester for corruptions. And this is pretty much the only kind of technique that we have for corruptions so far in this model. Okay, so now I would like to say, give the intuition about the lower bound for linearity testing. It's also not that hard. So every online erasure resilient linearity tester must make log T queries. So remember the T is the erasure budget. So here's the proof idea. So we can use the following strategy for the oracle. So erase T sums of previous queries of the tester in some specific order. So while you have the budget, just keep erasing sums of the previous queries. So if I make these queries, the adversary would erase the sum. I make another query, the adversary could erase the resulting sums here and the sum of all 3 points. And it keeps doing it while it can, right? So notice that if the tester makes more than fewer than log T queries, then Oracle can erase all the sums, right? Because there are fewer than 2 to the q sums. So the tester sees function values and linearly independent vectors from the domain. And the view of the tester is the same whether the input is a random linear function or a random function. And of course, for a random linear function, the tester has to accept. And for a random function, it has to reject because it's not hard to prove that the random function is far from linear. So this is the main idea of the proof. So, and now the question we can ask is, could we have used only pair queries in the tester, like in the BLR? And the answer is, yes, we could have used them, but then the dependence on T would be much worse. It would be at least, at best, T by a similar argument to this, because up to that many queries, the tester can keep erasing everything, right? So that connection, all the pairs formed by the current point and all the previous points that were asked, right? Okay, so we will get dependence T instead of log T. Okay, so now let me talk about low degree testing. So it's a generalization of linearity testing. So a function has degree at most D if it can be expressed as a polynomial of degree at most D in the corresponding variables. And so in the standard model, it has been studied extensively. So it has nice connections to PCPs. And the optimal tester is due to Dana and her co-authors. And the best lower bound is also due to them. And the subsequent paper by Bhattacharya et al. Improved the analysis of the tester so it matches the lower bound. So this is the query complexity of the tester, and it's optimal. So what do we have here? So first, notice that when T is constant, then the dependence on epsilon is pretty much the same as in the standard model. But the dependence on T is logarithmic here, and we have a logarithmic lower bound also. So there is some discrepancy between the exponents here, but roughly speaking, morally, we need the polylog dependence on T. So what's this tester? Okay, just thinking whether I should explain it. Okay, so let me say it, what it is. So it samples d+1 points from the domain, and then it queries F on all their linear combinations and rejects if the sum of the returned values is not zero, right? Because it's supposed to be actually zero for all low degree functions. So for example, if you want to test for quadraticity, you would query, so quadraticity d is equal to 2, so you query 3 points and all their linear combinations, and then reject if the sum of the returned values is 1. And again, it's very clear here that there are many dependencies and many opportunities for the Oracle to screw things up if you're trying to run exactly this test. And so the Minzer Zheng paper has a really, really beautiful idea of how to obtain a very nice tester. So they show that for low degree setting, there are also many options. So it's much harder to prove than for linearity. So there are many low degree tests. And so if you pick points uniformly and independently inside an affine subspace of large enough dimension in terms of T and D, then you can, with high probability, find a tester that uses these points. So you can basically make uniformly random queries inside some affine subspace and then be able to test based on that. Okay, so again, it gives a new tester for the standard model, even though their goal was to study online model. So like, okay, so what's a tester? It's so like, so there is some basically linear type equation that has to be satisfied on these points. And if it's not satisfied, so basically large enough fraction of points have to, so large enough fraction of points have to violate this equation if the function is far. So like in linearity, we have a tester based on pairs, tester based on 4 tuples and so on. So they're more complicated in the case of low degree, but there are many of them. So the running time is right. So like you have to try them, but the running time I think is not too bad. But you basically kind of try to solve for what you can do with the random points that you sampled. Okay, so now I'm going to talk about the impossibility of sortedness, unless there are questions about this. So, so here is the definition of the problem. So an array represented as a function from the indices to, let's say, natural numbers is sorted if f of x is less than or equal to f of y for all x less than y. And so in the standard model, of course, there is Dana's paper here, right? So we have pinned down the query complexity completely, right? So it's a log epsilon n over epsilon queries. And for uniform queries, it's a square root of n, so still sublinear. And in this other offline models, it's pretty much logarithmic, right? So like, so logarithmic here. And this is a wonderful paper, like a breakthrough by Sachs and Sesh, that roughly speaking, the dependence on n is logarithmic. I'm not going to say what epsilon represents here. So, and it turns out that in the online model, you cannot test it at all. So why? So let's look. So this is one example, hard example for sortedness that's often kind of used in lower bounds. So you can take a sorted array filled with numbers 1 through n, and then swap every odd position with a subsequent position. So as shown by this red segments. So then every position, so every pair represented by this red segments is violated, and there are no other violated pairs there. And now, as soon as the tester queries some point, the Oracle can erase the point that's paired up with this, right? So the tester, even if it queries half of the array, right? So at that point, the other half is going to be erased. It's never going to see any violations. So you can turn it into a formal proof, right? So this array is 1/2 far from sorted, but an online tester will see no violations. So here all violations are disjoint, and linearity and low degree testing violations overlap with each other. So there is something going on here in terms of the structure of violations. Okay, I think I'm running very badly on time. So sorry, so I talked about the first part. So separations between the models. Okay, so let's, for comparison, look at relationships between online testing models, between offline testing models first. So in the offline testing model, at this point, the picture is very clear. So we know that everything that's tolerantly testable is also erasure resiliently testable and is also testable in the standard model. And moreover, the containments are strict. So by the paper of Fisher and Fortnow that was already mentioned, we can separate standard model from tolerant model. And at this point, the parameters in their construction have been improved. So we know there are properties that are testable with a constant number of queries in the constant number in the standard model, but require a linear number of nearly linear number of queries in the tolerant model, right? And there are similar separations, standard versus erasure resilient, and erasure resilient versus tolerant. So we have a very clean picture, and we have beautiful connections to PCPs and locally decodable error correcting codes and so on in this line of work. So what can we say about separations between the online and offline models? Well, so first of all, we already saw that sortedness is testable with offline erasures, but not with online erasures. So is the online erasures model strictly harder? Right, so a priori, it's not clear. So on one hand, the erasures are happening online, so this is harder. On the other hand, we have much more erasures in the offline model, right? So constant fraction of points are erased. So this is when the interesting setting is, right? And in the online model, we have fewer erasures per query. So it turns out that the answer is no. There is a query separation in the other direction. So this is new work with Esty and Ephraim. So here's the picture we have. So sortedness is here. So it's testable in the offline model, not testable in the online model. So we know linearity is testable in both. And we give a property P, which is artificially constructed, right? So based on the PCP techniques, which is testable in the online model, but is not testable in the offline model. So specifically, there's a property, so for all settings of parameters, there is a property on n-bit strings such that P is online erasure resiliently testable with T erasures per query with a constant number of queries. And in the offline erasure model, so any tester that works for it with alpha fraction of corruptions needs a number of queries, which is basically linear in N. So this is one separation. So another question that we ask is about randomness. So you can see that all the testers we've presented so far, they have use much more randomness than in the offline model. So you can ask whether it's intrinsic or not. And basically the answer is yes. So there is a randomness separation. There is a paper by Oded Godrich and or Sheffet that basically says that in the offline models, only a logarithmic number of random bits is needed. So it's true about, so roughly log n bits are needed in all offline models. And what we show is that there are properties for which it's not the case in the online model. Right? So there exists a property P, which is testable with the same query complexity in the online and offline model. So this requirement there is to avoid some trivialities, basically. And log n random bits are sufficient offline, but you need n to some constant number of bits in the offline model. So there is a randomness separation. We need much more randomness in the online model. Okay, this is about separations. So there is a more nuanced version of the model that we introduced to overcome this impossibility results on sortedness, because of course it's very unsatisfactory to have a model where you cannot test sortedness. So we consider batch queries. So basically you can ask a batch of queries and then the erasures are not made while you're querying the batch. And the rates of erasures less than 1. So for example, you can make an erasure every other query. And we also look at different types of adversarial strategies. So fixed rate is the one that I already defined. And you can also allow budget managing adversaries. So these are adversaries that get rights to erasure at some point, and then they collect these rights, and then they erase wherever they want. So let me kind of briefly show. So maybe I'm not going to define. Okay, let me try to define. So there's a class of properties which are called local properties, which are basically characterized by the sets of forbidden subsets. So you have a family of pairs A and B which are ruled out. And so this pairs cannot appear in the consecutive positions. So for example, for sortedness, the family of pairs that characterizes it is of the form AB, where A is greater than B. So, and for the Lipschitz property, so again, so their properties of arrays, and the pairs that are forbidden are pairs of the form AB, where A minus B, the absolute value of that, is greater than 1. So these are examples of properties like this. So both of these properties are not testable in the online model, even with one erasure. Omri, is he here somewhere? Omri proved, generalizing previous work, that all local properties are actually testable with the same complexity as sortedness in the standard model. And so what we show here is an interesting phase transition for local properties. So in this table, we have batch size. So this is 1, the model that we've been looking at. And here's the batch size 2. And the behavior changes drastically between them. And here's the fixed rate adversary and budget managing adversary. And there are interesting phase transitions corresponding to these regimes. So for fixed rate adversary, so we saw that it's impossible to test if you have even one erasure, for example, sortedness, it's impossible to test. So it turns out that this is roughly where the boundary is. So for any rate of erasures, any constant rate less than 1, you can actually test. And the query complexity, so ignoring this, is pretty much the same as before. And so here, the closer you get to 1, you see the higher the query complexity becomes, right? So, and I guess if you get to 1, it stops being testable. And if you have a budget managing adversary, so there is a transition that happens around theta of epsilon erasure rate. So it's impossible to test before and, after that, and before that you get the optimal query complexity. And the picture changes drastically if you allow 2 batches of size 2. So then you can basically test with the optimal query complexity up to basically linear number of queries. So these are kind of interesting phase transitions, and they also hold for corruptions. Okay, so last thing I'm going to just briefly mention is connection to maker-breaker games. Positional games are central objects studied in combinatorics. There are books written about them. And maker-breaker games are prominent and widely investigated example. And so what's an Esty maker-breaker game? So it has 2 parameters, S and T. And it's defined by a finite set X of board elements and the family of winning sets. So each such winning set is a subset of the board elements. And 2 players, maker and breaker, take turns taking unclaimed elements of X. And maker makes S elements on each turn, and breaker claims T elements on each turn. And the maker wins if she manages to claim all elements of the winning set. Otherwise, the breaker wins. Right? And tic-tac-toe, if you don't allow the draw, is an example of such a game. And I just wanted to kind of mention that in online testing, we have like an analogous situation. So algorithm is the maker, adversary is the breaker, and then the main of the input function is the set of board elements, and the witnesses are winning sets. So the big complication is that the tester does not know in advance which sets are winning, right? Because even if it collected for linearity, let's say x, y, and x plus y, it doesn't mean that it's going to be a witness. So this is a complication. But a prerequisite for designing an online tester is identifying the set of winning elements and a winning strategy for the maker. So at the least, you should be able to collect the right type of, the right set of board elements of queries, right? So, oops, sorry. So we hope that online erasures model motivates studying new maker-breaker games, right? And you can also see that they have a general SNT, so that corresponds to batch queries, right? And allowing arbitrary number of queries, also erasures after each query. Okay. So I talked about all the things. So I hope I have time just to say some open questions. Okay. So first of all, online manipulation resilient testers for specific properties would be interesting to design, right? So we have some, but not that many. So investigation of the for the threshold T, I think, is an interesting direction in kind of phase transitions. So what's the maximum T max for which a given property is testable, and what exactly is happening to the query complexity as we approach T max? So is the transition somehow smooth, or what's happening there? So another question is some general characterization, perhaps, of properties testable with online erasures, and somehow maybe you can understand something in terms of the structure of the witnesses. And the fourth one is more techniques for online corruptions. So far, as I mentioned, all testability results are for algorithms that are unlikely to see a manipulated point, but this is not the case in the tolerant testing model, for example, right? So there is somehow we have testers that can see corruptions, right? And they do just fine. And so the final question is just trying to study other sublinear time algorithms. So the model is not really specific to property testing, but property testing just gives us like a really clean problem to handle, but we can study more general sublinear time algorithms also with online erasures. Thank you, and happy birthday, Dana. And again, so I guess I'll say a little more later.
Right, so is there any question on Sofya?
So if I want to study this modeling graph property testing, is there some suitable? So have there been any results of this sort?
So we're thinking about it actually with Ephraim, who is sitting in front of you. So we're thinking about it, but I guess we have some little bit of partial results, but the model fits, right? Like you can, yeah, so there are results in the offline model for sure, but in the online model, there's nothing studied yet. So if you're interested in working, we're happy to talk to you, right? So. I'll pick up other stuff, right?
Okay. So while Kalemaj is setting up, I think it's a great opportunity to thank him for, yes, thank you, for helping in organizing this semester.